Alright, so this is video project 4 for ME210, and we will be talking about a soccer ball versus a wall. In this video, we'll analyze impulse and momentum based on chapter 15, and using that impulse and momentum, we will be figuring out a soccer ball bouncing off a wall, and we'll be calculating its impulse, average force, coefficient of restitution, and we will also be looking around how changing the contact time between the ball hitting the wall and coming off affects its impact force. Here we have the scenario where I am kicking the ball towards the wall, and we are recording to calculate the amount of velocity that the ball is first started off with, going towards the wall and coming back towards the wall. So here we'll have the video play. Do it one more time just because it's a little laggy, but you can see I kick it and it comes straight back to me. And on the bottom left I have like a design diagram of the measurements and everything. So I have 15 feet between where I stand to the wall, and then I have the labeled velocities where it's positive going to the right towards the wall and negative coming back towards me or towards the left coming off of the wall. So I have the ball mass. It's a FIFA regulated ball, so I have some research through that, and it was about 0.43 kilograms. And then the incoming speed, which is velocity going towards the right. Throughout the video, I recorded it and went frame by frame to see the time it took to go from start to the wall, and calculated that using distance over time, which gave me 30 meters per second. And then the rebound speed, so the speed coming from the wall towards me again, doing the same exact thing, distance over time, 11.5 meters per second. And I did I did some like tedious frame by frame seconds to calculate the time that it was on the wall itself. iPhone also has like this like frame meter, like the frames per second like calculating thing, where you can see how long each frame is in motion for, and it came out to be about 0.00667 seconds that the impact time was. So here we just have another example of the velocities coming towards the wall and coming off the wall, and just the measurement itself. And you can see that it just comes straight from where I stand to the wall and straight back. And using these measurements, we could start to calculate the rest of everything else. So here we have the calculations where we have the givens from the past slide, and then we have the formulas to find the impulse, the coefficient of restitution, and the average impact force. So we know to solve for impulse, the equation is J is equal to m, which is the mass, times the velocity going towards the wall minus the velocity coming back towards me. And once we plug everything back in, we know that the mass is 0.43, and then we subtract, kind of add the velocities together, we get that the impulse is 17.85 newtons, meaning 17.85 newtons is reduced from the initial contact or initial impulse going towards the wall. And then to solve for the coefficient of restitution, where we have the equation E is equal to the absolute value of V2 over V1, when we plug in our velocities, we get it's 0.383, which is 38.3%, meaning 38.3% of the ball's velocity going towards the wall. Only 38.3% of the velocity is coming back off the wall when its initial velocity is 30 meters per second. And then to calculate the average impact force, we have the equation is F average is equal to the impulse over the delta in time, which if we solve for the delta in time, which is where we calculate the contact time, we know, well, I did the tedious work of seeing that there was 2 frames and it was recorded in 30 frames per second, so that's how I got the contact time. And once we plug that back into the F average equation, which is the impulse over the time delta, we get F average is equal to 268 newtons. And then to find the force peak of it, we just multiply that by 2, which turns out to 536 newtons. So these results basically just show that the impulse is the same regardless of how quickly the ball is compressed and rebounds. But with longer contact time and same impulses, it produces a smaller force. If this had been a stiffer or like a less like or a more compressed ball, meaning there was more air in the ball, or a faster contact, say 8 milliseconds between the contact time of the ball getting into the wall and then releasing back off of it, the average force would jump around like 2.2 kilonewtons. So there's just like this like slight difference in everything, and the peak force would be like 4.5 kilonewtons, even though the impulse stays about the same at 17.85 newtons per second. So there's just like this like difference in the impulse and everything, or not the impulse, sorry, the peaks and average of the force based on like the stiffness or the compression of the air inside the ball, or how fast the ball is getting kicked towards the wall. So by using the impulse momentum theory or theorem, and like calculating all the data and velocities based on the video, we can see that increasing contact time dramatically reduces force, and the same principle of that protects how we could calculate everything else based on inflation of the ball and all those other small details.